Okay, let's dive into message queues. They are super important for understanding how WebSockets handle real-time data. Basically, a message queue is like a post office for messages. When something happens and needs to be communicated, instead of directly sending the information to another part of the system, we put it in this queue. A producer, which is like someone sending out a notification or an event, adds the message to the queue. Then consumers think of them as workers who need to process that information, pick up messages from the queue whenever they're ready. This means the sender doesn't have to wait for a response, making things faster and more responsive. Plus, it helps scale well because you can add more consumers if needed, and it ensures that no message is lost. Okay, so let's talk about how message queues actually make our lives easier. Basically, they solve a bunch of headaches that come up when multiple services need to chat with each other in real time. The biggest challenge often is getting things done asynchronously, meaning one service doesn't have to wait for another to respond before continuing its work. They just drop the message off and let it go. And because these services aren't directly connected, they're loosely coupled, so if one breaks down, it doesn't necessarily bring everything else crashing down. Plus, messages are kept safe until they're actually processed, ensuring nothing gets lost, even if a service is temporarily offline. Finally, they handle spikes in traffic really well, allowing our systems to scale up and down smoothly. Okay, let's talk about RabbitMQ. It's a really important piece of the puzzle when we're talking about real-time communication and building robust systems. Basically, it's like a super efficient post office for your applications. You have publishers, these are apps that send messages out, and subscribers, which are other apps that want to receive those messages. Messages don't go directly from one app to another. They first go through the RabbitMQ broker, or post office. It stores them in queues until a subscriber is ready. Then, it routes them according to rules, ensuring the right message gets to the right place. This decoupling makes your system much more scalable and reliable because components can work independently without being tightly coupled. Okay, let's talk about Apache Kafka. It's a really important piece of the puzzle when we're discussing real-time communication. Imagine you have lots of different applications all trying to send and receive information quickly. Kafka acts like a central hub for that data flow. It's not just a regular database or message queue, it's designed specifically for handling continuous streams of events. Think of topics as categories, like folders in your email. You have one for sales emails, another for marketing, etc. Each topic is then split into partitions to allow multiple producers and consumers to work with the data simultaneously, making it super scalable. Producers are apps that send information ** to ** Kafka, and consumers are the apps that pull that information ** from ** Kafka. It's all about building reliable, real-time pipelines. Let's talk about a common question in interviews: how do RabbitMQ and Kafka compare? Think of RabbitMQ as being great at managing individual tasks. It's like a reliable post office that directs messages to the right place based on complex rules. On the other hand, Kafka is built for speed and scale. It handles huge streams of data really well, almost like a continuous conveyor belt. It's excellent when you're dealing with things like real-time analytics or building systems where data needs to flow quickly from one point to another. Key differences lie in their architecture. RabbitMQ is a traditional broker, while Kafka uses a distributed log system. And importantly, they handle ordering differently. RabbitMQ guarantees order within each queue, while Kafka offers a partition within the log. Okay, let's dive into the guts of RabbitMQ. Think of it like a postal service for applications. At its core, we have exchanges. These are where messages ** arrive ** and get routed. Then there's the queues themselves, which hold those messages until someone wants them. Bindings act as the instructions, telling the exchange exactly which queues to send messages to based on certain rules. You've got publishers sending the letters messages to the exchange, and subscribers are the recipients who actually read and process those messages. Okay, let's talk about the foundation of Kafka, its key components. At its heart, you have brokers. These are the servers that actually store your data. Think of them like robust filing cabinets. Then there are topics. These act like categories or feeds where all related messages get grouped together. Kafka then divides those topics into partitions for increased speed and reliability, handled by multiple brokers. Producers are applications pushing data asterisk into asterisk Kafka, while consumers pull it out to process it. And finally, Zookeeper helps manage the whole system, though Kafka is evolving to reduce its reliance on it. Okay, let's talk about producers and message queues. Basically, a producer is like the starting point in application or service that's responsible for creating and sending messages into the queue. It's not waiting around to see if someone picks up that message, it just puts it there and moves on. Think of it as generating data, formatting it into a message, and then dropping it off at the queue. A good example is when you submit a form on a website. That form submission asterisk is asterisk to the producer, sending its data into the queue for processing. Okay, let's talk about consumers and message queues. Basically, a consumer is an app or service that's actively looking for messages and then doing something with them. Producers send the messages out. Maybe it's an order being placed, a new user signing up, or some sensor data. The consumer picks up those messages when it's asterisk ready to handle them. They subscribe to specific queues or topics so they know what messages are relevant to them. Once they receive a message, they process it. That could mean updating a database, sending an email, or any number of things. The cool thing is, consumers operate independently and can easily scale up or down as needed. It's a really powerful way to build decoupled systems. Okay, let's talk about message brokers. Basically, they're like a post office for your applications. Without a broker, if two different parts of your system need to talk to each other directly, it can create a tangled mess and make things really complicated when you want to change something. A message broker solves that by acting as an intermediary. It's one service that both services talk asterisk to asterisk, but they don't have to know about each other directly. This makes your system much more flexible and easier to manage. Okay, so let's talk about queues and Routed-MQ. Imagine a really busy restaurant. That's essentially what a queue is like. Producers are like the customers putting orders in. They send messages to the queue. The queue itself just holds those messages until a consumer is ready to pick them up and fulfill the order. This keeps things super organized and makes sure nothing gets lost, which is vital for reliable real-time communication. Understanding queues is key to grasping how WebSockets can scale and handle a lot of information smoothly. Let's talk about Kafka topics. They're really the core of how this system works. Think of a topic as a named category or feed for all your data. It's similar to a table in a database, where each row is a message being sent. You can name these topics based on what kind of information they hold, like user activity or order events. And here's the really clever part: topics can be split into partitions, which allows Kafka to handle huge amounts of data efficiently and reliably. It's all about organizing and distributing your data in a smart way. Okay, let's talk about partitions in Kafka. They're super important for understanding how it works and why it's so scalable. A partition is essentially a single slice of data within a topic. Think of a topic like a category, maybe user activity, and then each partition holds one specific set of user activities. Each message has to have the same key, which determines which partition it goes into. This ensures related messages stay together. Because you can have multiple consumers reading from different partitions simultaneously, Kafka's able to handle massive amounts of data really quickly. Okay, let's talk about how Kafka makes sure messages arrive in the correct order. It's not always straightforward because it's designed for high throughput and scalability. The key thing to understand is that Kafka guarantees ordering with an a single partition. Every message sent to the same partition will be delivered to your consumers in the exact order they were produced. Producers keep track of their messages with offsets, and consumers also do, ensuring things stay consistent within each partition. It's like a very organized internal postal system for that specific part of your data stream. But remember, if you're using multiple partitions, you won't have ordering across them. Okay, let's talk about how RabbitMQ handles message order. It's a really important detail to get right. By default, messages can sometimes arrive out of the order they were sent. It's not guaranteed. There are a few ways to ensure that messages arrive in the intended sequence. One simple way is to use just one queue per exchange, but this limits how many people can handle the messages at once. A more scalable approach is using clustering and creating separate queues for each exchange. Another option involves publisher confirms and transactions, which can guarantee order but might impact performance a little bit. It's all about choosing the right strategy based on your application's needs. Okay, let's talk about consumer groups in Kafka. They're really important for making your real-time applications scalable and reliable. Think of it like this. You have a bunch of teams that need to process the same data coming from Kafka, but instead of each team pulling its own copies, we use consumer groups. Essentially, a consumer group is just a collection of consumers working together. Each partition in a topic gets assigned to only *1 consumer within that group. That means you can have multiple consumer groups all reading from the same topic at the same time, so you're not competing for resources and you're able to process data much faster because they can work in parallel. And if one of those consumers has a problem, the others keep going, ensuring your system stays running smoothly. Okay, let's dive into durable queues in RabbitMQ. Essentially, a durable queue is like a really reliable inbox. Even if the server takes a nap, your messages aren't lost. It works by telling RabbitMQ to save information about the queue on disk, so when it comes back up, it knows exactly where to find those messages. You declare a queue as durable when you create it, and that ensures its persistence. They're super important for building robust real-time systems. Okay, so let's talk about message acknowledgements in RabbitMQ. Basically, it's a way for the consumer to tell the producer that they've actually received and successfully processed a message. It's super important for reliability. Think of it like this: just because a message arrives doesn't mean it was handled correctly. RabbitMQ uses what's called a publish acknowledge pattern. If you send a message, you can tell RabbitMQ to only deliver it if the consumer confirms they got it and worked on it. There are two types: automatic acknowledgement, which is convenient but less safe, and explicit acknowledgements that require the consumer to send back a confirmation. And if a consumer fails to acknowledge a message within a certain time frame, RabbitMQ moves it to a dead letter queue for you to investigate and potentially resend later. Okay, let's talk about message retention in Kafka. It's a really important concept for anyone working with the system. Basically, Kafka doesn't just shove data into storage and forget about it. It keeps things around. The retention MS setting controls how long messages are stored, measured in milliseconds. It's often set to indefinitely by default, which means they stick around until we explicitly delete them or Kafka automatically compacts the logs to free up space. And that compaction, it's like a cleanup process that combines older data into newer chunks, making things more efficient. When answering interview questions, be sure you understand how the setting impacts both storage costs and system performance. Think about the difference between keeping messages forever versus having a set expiration time. Okay, let's talk about dead letter queues. They're a really important concept for building robust real-time applications using WebSockets. Basically, imagine you're sending lots of messages back and forth, and sometimes those messages just don't make it through. Maybe there was a temporary network problem, or the server had a hiccup. A dead letter queue is like a catch-all for those failed messages. It's a special queue that collects all the messages that couldn't be successfully delivered after several attempts to retry sending them. This prevents data loss and makes it easier to figure out what went wrong, so you can fix any underlying issues and keep your system running smoothly. Okay, let's talk about fan-out exchanges in RabbitMQ. Imagine you have a central hub. That's what a fan-out exchange is like. When a message comes through, it doesn't care where it goes, it just blasts out copies of that message to every single queue that's listening. It's like shouting into a megaphone, and everyone within earshot hears the same thing. This is great for things like instant notifications. If someone signs up for an account, you want everyone who subscribed to receive that notification at once. Okay, let's talk about direct exchanges in RabbitMQ. Essentially, a direct exchange is like a very strict gatekeeper for your messages. It only lets through messages that have the exact same key as one of its bindings, which are links to queues. If the routing key doesn't match, the message gets tossed aside entirely. This makes them really useful when you need a simple, direct connection between two parts of your system, like sending a comment from one user straight to another's display. Okay, so let's dive into topic exchanges in RabbitMQ. Imagine you have a direct exchange. It sends messages only to queues that exactly match the routing key. But what if you need more flexibility? That's where topic exchanges come in. They use wildcards like and hash to route messages to multiple queues at once. It's like having a flexible filter system. The matches anything before the binding key, while the hashtag matches anything after it. This means one message can go to several different consumers depending on how the queues are set up with those routing keys, which is fantastic for building really dynamic and scalable applications. Okay, let's talk about headers exchanges in RabbitMQ. They're a really powerful feature that sets them apart from standard exchanges like direct or topic exchanges. Instead of routing messages based on the content within the body like a direct exchange does, a headers exchange looks at the keys and headers attached to the message itself. It's essentially saying ignore what's in this message, just route it if it has these specific routing keys or headers. It gives you an amazing amount of control over how your messages are delivered. Okay, so let's talk about how messages are handled in real-time systems. We often encounter two main patterns, point-to-point and publish-subscribe. Point-to-point is like a direct phone call. One sender talks directly to one receiver. It's simple to understand and implement, but it can get complicated if you have lots of people involved. On the other hand, publish-subscribe is more like a newspaper. Anyone interested in a specific topic, the topic or channel, can subscribe and receive all messages related to that topic, without needing to know who published them. This creates a lot of flexibility and scalability, but it requires a bit more setup, usually a message broker, to manage everything. Okay, let's talk about back pressure. It's a really important idea when we're building real-time applications. Imagine you have a system that's constantly pushing messages out. If the person on the receiving end can't keep up, things start to break down. That's where back pressure comes in. It's like a traffic jam. Too much flow overwhelms the whole system. Without it, you risk losing data or even crashing your entire application. We use techniques like rate limiting, queuing messages when things slow down, and sometimes even circuit breakers to protect our systems from overload, basically making sure nothing gets dropped or corrupted. Okay, let's talk about how Kafka makes sure your messages stick around. It's all about redundancy. Kafka uses replication, meaning each piece of data gets copied several times across different servers. Think of it like making multiple copies of an important document. Then there are offsets. These are unique identifiers for each message, essentially a log pointer telling us where the message is in the stream. And finally, Kafka keeps track of which servers called ISR are keeping up with the main server or leader. If that main server goes down, and it will eventually, another ISR automatically takes over. Consumers don't lose their place, they just keep reading from where they left off. It's a really clever system that guarantees your data isn't lost even when things go wrong. Okay, let's talk about replication in Kafka. It's a really key concept for understanding how robust and reliable this system is. Think of it like having multiple copies of your data stored across different servers. Each topic is broken down into partitions, and each partition gets replicated to several other brokers within the cluster. So, if one server goes down, there are others ready to pick up the slack and keep things running smoothly. This redundancy means your data isn't lost, it's incredibly durable, and you can also read from multiple places at once for even faster performance. That's the power of Kafka replication. Okay, so let's talk about offsets in Kafka. Basically, an offset is like a bookmark for each consumer. It tells Kafka exactly which message that particular consumer has already read from a topic's partition. It's crucial because consumers might process data at different speeds, and the offset ensures no messages are lost or reprocessed. Okay, let's talk about how Kafka keeps track of where it is in a stream. That's what we mean by offset management. Basically, every time a message arrives and gets processed, Kafka assigns it a number. Think of it like page numbers in a book. Consumers, which are the programs reading these messages, need to know the current page or offset so they don't miss anything or reprocess data. Kafka's broker, the central server, handles this for consumer groups. It remembers the last offset committed by each consumer within each partition. So, if a consumer fails and restarts, it can pick up right where it left off because it knows exactly where to start reading again. There are two main ways consumers get this information. They can ask Kafka pull-based, or Kafka can push the next offset to them push-based. It's an important detail for ensuring your data is processed reliably and consistently. Okay, so let's dive into idempotency. It's a really important idea when we're talking about building reliable systems with message queues. Basically, an operation is idempotent if doing it again and again gives you the same outcome as doing it just once. Think of it like sending the same instruction to a computer twice. It should still do what it was supposed to do. In a message queue environment, messages can sometimes be delivered more than once because things don't always go smoothly in the network. If we're not careful, duplicate messages could cause problems. Imagine placing an order twice, or getting charged for the same thing twice. To avoid this, we need to ensure our processing is idempotent, meaning that each time a message arrives, it processes correctly as if it were the first time. We can achieve this by using unique identifiers like order ID and carefully checking for existing records before creating new ones. It's all about building systems that are resilient to those occasional hiccups. Okay, let's talk about exactly once delivery. Think of it like making sure every single message gets processed only once, even if things go a little sideways like network glitches or server crashes. It's super important because you don't want to accidentally process the same order twice or lose critical data. We achieve this by building our message handlers to be idempotent, meaning they can handle the same message repeatedly without changing anything. We also use unique identifiers for each message, like sequence numbers, so we can spot and discard any duplicates. And for more complex operations that involve several steps, we might use something called a two-phase commit protocol to ensure everything either succeeds completely or gets rolled back entirely. It adds some complexity, but it's essential for building reliable real-time applications. Okay, let's talk about something super important when it comes to WebSockets delivery guarantees. We have two main concepts here, at most once and at least once delivery. At most once means a message gets through exactly once, but there's no guarantee *1 that will be. It's like sending a postcard. You know it'll eventually arrive, but things can go wrong. Then we have at least once delivery. This guarantees the message makes it through at least once, even if it means trying again if something goes wrong. This is more complex and could lead to duplicates, but it's vital for applications where you absolutely need to ensure a message gets received, like financial transactions or critical updates. It's all about weighing the simplicity of at most once against the reliability of at least once. Choosing the best fit depends on what your application needs. Okay, let's talk about how WebSockets handle message delivery. There are two main goals: making sure messages arrive and ensuring they only happen once. At least once delivery means we'll get the message eventually, even if it arrives more than once, like a reliable postal service that might send you a letter twice. This is easier to set up because we can just retry sending if something goes wrong. But there's a risk of duplicates. On the flip side, exactly once delivery guarantees each message gets through only once, which requires extra checks and processing, potentially adding some delay. It's more complex but ensures no data is lost or duplicated. Choosing between them depends on how critical it is to avoid errors and what you can tolerate in terms of speed. Okay, let's talk about how we send messages between a client and a server, specifically synchronous versus asynchronous messaging. Synchronous is like making a phone call. You ask a question, and you immediately get an answer back. It's great for things that need immediate feedback, like when you're filling out a form on a website. Now, asynchronous is more like sending a letter. You put it in the mailbox, but you don't wait there to see if it arrives. The server processes your message and can then move on to other tasks. This makes systems much more scalable because they aren't constantly waiting for responses. Let's talk about how we handle failed message delivers in RabbitMQ. When things go wrong, maybe there's a network hiccup or the broker is temporarily unavailable, it's important to keep trying until the message gets through. We can do this automatically by setting our exchanges and queues to retry, or we can build custom retry logic directly into our consumers using strategies like exponential backf. Basically, we start with a short delay, then increase that delay for each subsequent failed attempt, giving the system time to recover. Okay, let's talk about the really important aspect of building robust real-time systems. How do you handle poison messages? These are messages that are intentionally designed to cause problems, think corrupted data, or even outright malicious attacks. The good news is there are several approaches we can take. First, strong validation at both the sending and receiving ends is key. Catch as much as possible early on. Then, using a dead letter queue allows us to isolate suspicious messages for investigation without disrupting the entire system. Circuit breakers can help prevent failures from spreading, and retries with increasing delays can tackle temporary issues. Finally, requiring acknowledgements ensures that the receiver actually processed the message before we consider it successful. Okay, let's talk about message schemas. They're a really important concept in building robust real-time applications. A message schema is basically like a contract for how data gets passed between your client and server. It specifies exactly what information each message should contain, including the types of data, clear labels for those pieces of information, and even the order in which they appear. Think of it as a standardized form to ensure everyone's on the same page. Different formats like JSON, protobuf, or message pack are common choices, and selecting the right one will help you build something reliable and scalable. Okay, let's talk about schema registry in Kafka. It's a really important piece of the puzzle when you're building real-time applications with Kafka. Basically, it acts like a central contract for your data. Imagine you have different teams sending messages to the same topic with that schema registry. They might all use slightly different versions of what a message looks like, which can lead to chaos and errors. The registry stores these schemas, things like Avro or protobuf definitions, so that producers know exactly how to format their data, and consumers know exactly what to expect when they receive it. This makes evolving your system much easier over time because you can safely change the schema without breaking older applications. Okay, let's talk about scaling RabbitMQ, a really important topic in real-time systems. The key is to move beyond just adding more powerful servers. Clustering is absolutely fundamental. It allows you to distribute messages across multiple nodes for increased speed and reliability. Within the cluster, you'll want to think about how your queues and exchanges are divided. Charting them based on a key ensures that messages go to the correct server. As your system grows, you'll need to add more nodes horizontally. Keep an eye on queue lengths and node usage. Those are your signals for scaling up. And don't forget things like optimizing your queues and managing connections efficiently. All these little details make a big difference. Okay, let's talk about scaling Kafka. It's almost always going to come up in interviews. Think of partitioning as the first line of defense. Spreading your data across multiple brokers lets you handle *lot more traffic. Replication is critical for reliability, making sure you don't lose any data if something goes wrong. You'll also want to think about adding more brokers themselves. Managed services are really helpful here because they automate a lot of that. And remember, consumers need to be balanced across partitions so no single consumer gets overwhelmed. Finally, always consider how you'd react to a big surge in data. Increasing capacity and smartly managing those partitions is key. Okay, let's talk about RabbitMQ. It's a really important tool when we're thinking about real-time communication, especially when you're combining it with WebSockets. Basically, it acts as a central hub for messages. Think of it like this: instead of every service needing to constantly check each other to see if there's something new, they send a message to RabbitMQ, and then RabbitMQ figures out where that message needs to go. This is hugely beneficial for things like building live chat apps, making sure those instant messages get delivered quickly. It's also great for sending alerts in real time, processing data from IoT devices like smart thermostats or industrial sensors, managing orders in e-commerce systems, and even handling communication within multiplayer games. The key benefit here is that it keeps everything decoupled, so if one part of the system has a problem, it doesn't bring down the whole thing. Okay, let's talk about why Kafka is so popular. Essentially, Kafka is a super speedy messaging system designed for real-time data. It handles huge volumes of information flowing from lots of different places: websites, apps, sensors, you name it. One really common use case is doing instant analytics. Imagine tracking every click on your website and instantly seeing trends appear in a dashboard. Then there's log aggregation, where Kafka can collect all the logs from your servers to make debugging much easier. And because it's built for speed, it's great for real-time processing things like spotting fraud or making personalized recommendations. It's also used for building complex systems that rely on events, so services can talk to each other without being constantly tied together. Okay, let's talk about monitoring those message queues in your WebSocket applications. It's super important. First off, you need to keep an eye on the depth of the queue, how many messages are waiting. A steadily increasing depth is a huge red flag, usually meaning something isn't processing quickly enough. Then check the age of messages. If they're sitting there for too long, it suggests your consumers aren't keeping up. Tracking processing time how long each message takes to go from being added to being fully processed will help you spot bottlenecks. And don't forget to monitor those error rates. Logging with structured data is key. Think JSON logs that make it easier to pull metrics out of your system and analyze them. Okay, let's talk about keeping our message queues safe. It's really important because if someone gets in, they can potentially disrupt your whole system. First off, you need a solid way to verify who is sending messages. Think of authentication and authorization. Then, always encrypt the data both when it's traveling through the network and when it's stored. Rate limiting prevents attackers from flooding your system with requests. Don't forget to validate all incoming messages, make sure they're what you expect and don't contain anything malicious. And finally, keep everything locked down, restrict access to the queue server and monitor for any suspicious activity. Okay, let's talk about message ordering. It's super important when you're building real-time apps that need to feel responsive. The problem is, when messages travel across multiple servers, they don't always arrive in the order they were sent. It's like sending a series of postcards and hoping they arrive in the right sequence. So, how do we tackle this? We can use things like sequence numbers, giving each message a unique number so the receiver knows where it fits in the overall stream. Timestamps are also useful, letting us know when messages were actually sent. For truly robust ordering, you might look into consensus algorithms like Raft or Paxos, but those are more complex and can sometimes slow things down. Finally, causal ordering. If message A calls message B and it has to be processed before B, that's a good balance between order and speed. Okay, let's talk about stream processing in Kafka. It's a really important part of how Kafka is used. Basically, instead of waiting for batches of data to come through and then processing them, you're analyzing the data as it arrives, almost like a continuous factory line. Kafka Streams is the tool we use for this. It lets us build stream processing applications right within our Kafka cluster. You can have stateless processes, which just do simple transformations on each piece of data, or stateful processes that remember things and update them over time. We also use something called windowing to group events together, like looking at the last 5 minutes of transactions. And we have triggers and transformations where we define rules based on what's happening in the stream. For example, if a transaction is unusually large, it might trigger an alert. A good example would be fraud detection. You can analyze transactions as they happen to catch suspicious activity. Okay, let's talk about how we integrate message queues into our microservice architecture. The core problem with other queues is that services are tightly linked. If one goes down, others can be affected. Message queues solve this by introducing asynchronous communication. Think of it like this: instead of a direct phone call, you send a letter through the mail. The receiving service isn't immediately available. It's fine. The message sits in the queue until it can be processed. This decouples services, making them more resilient and able to handle traffic spikes much better. We often use popular options like RabbitMQ or Kafka, each suited for different needs from complex routing scenarios to high-volume streaming. Okay, let's talk about some of the downsides you might run into when thinking about RabbitMQ and Kafka for real-time apps. RabbitMQ is really built as a message queue. It excels at getting messages from point A to point B reliably. But because of that focus on durability, it isn't always the best choice for super fast data streams or complex events. Scaling can also get tricky. Now, Kafka is fantastic for streaming data, think continuous updates and things flowing really quickly. However, its log structure means you generally can't easily go back to a specific point in time within that stream. And managing those offsets, keeping track of where you are in the data flow, is something you need to get right, or you could run into problems. Both systems have their own operational challenges too when dealing with really large clusters, and managing state outside of these systems often requires extra work. Thank you for watching.